Okay, so today my talk for around 40 or hopefully a bit less than 40 minutes, my plan is to show you how we can ensure, or to give a glimpse on how we can ensure some of the key requirements for trustworthy AI, in particular for federated learning, via a principle that is known, or that I call total variation minimization. So this TV minimization is the basic engine, so to say, that I will use to implement trustworthy federated learning. Okay, so just to put it into perspective, federated learning as a special case of machine learning. So here's my one slide about machine learning, plain old machine learning. So we have this famous three components of machine learning. We have data. In this case, we load data from a toy data set from Python. We have a model in the sense of different hypothesis maps. So we always need more than one hypothesis map in order to learn something. And yeah, we learn a hypothesis map, or we train the model, or we fit the model by minimizing a loss function. So minimizing this average loss here. And you see here these three components are tied together. We have the loss function, which is a design choice, somewhat hidden in this decision tree classifier class. We have data, we read in data, for example, here this iris flower data set, and we need a model. So we need to specify what is the set of hypothesis maps. This is also done by using this decision tree classifier. So that's nice. That's the basic setup of machine learning. And I would say this shows, or this depicts the basic idea of 99.99999% of what is currently branded or sold or hyped as AI and machine learning. Okay, so let's drill this a bit more down. So in reality, it might look maybe like this. For example, when you have smartphone apps. So often doing an application means doing an app, a smartphone app. So also for machine learning, we can do apps. And here we already see that we not only have one computer, but we have a whole collection of computers, or a network of computers. So here's already intrinsic a network structure. We have smartphones connected via Bluetooth. So when you are nearby to each other, when you have physical proximity, this was relevant for COVID tracking apps. So we had the network structure given by contact networks. We have a network structure given by mobile phone networks or mobile phone operators. And also sometimes we use the cloud. So there's really a heterogeneous mix of models or of computers, and each computer per se could have its own data set. So each one of us has a smartphone app that does a fitness tracking. So we collect our own data. We have a local data set, and we also want to learn a local model, or we want to train a local model. I want to learn a fitness trainer app for me that is optimized for me, and not for the average person. I want it optimized for me. So we train models for each node in a network. Okay, so before I formalize this federated learning setting with what I call total variation minimization, I would like to highlight some of the key requirements. We often, at least I must say, I mainly think about when it's about designing solutions for such federated learning applications, about statistical aspects. So I want to have models that are accurate, and computational aspects. I want these federated learning systems to use as little computation, as little battery as possible, to be as robust as possible to network failures or Bluetooth connection errors. So there's always this statistical and computational view or perspective. However, I recently started to appreciate the third view, which is actually maybe the most important one, which is the human perspective. So we want these federated learning systems to serve us humans. So I would like to remind you about some of the key requirements for trustworthy artificial intelligence. And I here would like to ask you if you could raise your hand or drop a ping on the chat. How many of you have heard about these 7 key requirements for trustworthy AI? So these key requirements have been formulated by an expert group that has been organized by the European Union. So how many of you have heard about this? For how many of you does this ring a bell? 7 key requirements for federated or for AI. Yes, so there are a few hands up. Yes, a few, but I would have hoped more. So we tend to focus on this hard mathematics like convergence rates or proving consistencies. So this is all statistics and numerical linear algebra. But I'm a big fan of bringing also this requirements for the user perspective into play here. So it was very important for me to show you this slide here today. And so I will focus on 4 requirements, the 4 first ones, which are human agency and oversight, technical robustness and safety, privacy and data governance, and transparency. The other 3, I cannot really tell much about because I'm still trying to understand exactly what they mean. But for the first 4, I have some idea because it's related to engineering. So the first one is requirement 1 is human agency and oversight, which I cite here this high-level expert group document, which I put the link there in the slide. So here it says AI systems should empower human beings, allowing them to make informed decisions. At the same time, proper oversight mechanisms need to be ensured. So we must have some way to have oversight to somehow know what is going on. And I will show you how we could do this with GTV minimization. Second requirement is the technical robustness and safety. Here it states AI systems need to be resilient and secure. They need to be safe, as well as being accurate, reliable, and reproducible. So this accurate might be not so strange to you. Accuracy. We want high accuracy or minimize error rates. So this is reasonable. Reliability. So this is related to outliers, to attacks maybe. And reproducibility, this might be related to something that we could measure with variance. So this is actually quite close to our home turf as engineers or machine learning scientists. Also, privacy and data governance is a key requirement. So adequate data governance mechanisms must also be ensured, taking into account the quality and integrity of data. And the 4th requirement I will sketch, or I will discuss in the context of federated learning, is transparency. So the data system and the AI business model should be transparent. Moreover, AI systems and their decisions should be explained in a manner adapted to the stakeholder. So here, what I find remarkable is already a hint that the explanation or explainability in machine learning is something personalized. Explanations must be or should be adapted to the stakeholder. Like what I do now in my talk is I explain something to you. I explain how you can do trustworthy federated learning with GTV minimization. And my explanation, I only give one explanation. I only give one talk. I cannot do parallel talks yet. But it's designed to meet somewhat the average of you. So some of you might have, for some of you, it might be too difficult. For some of you, it might be too boring because I cannot adapt my explanation here in this case because I only give one talk. Okay, so now I would like to introduce this federated learning design principle. Yes, the comment or just an open mic? Okay, so this federated learning design principle that I was talking about is, of course, based on the 3 main components of machine learning and federated learning. So first, we need data. So in federated learning, we typically face network data. So there's not one data set, but there's a collection of data sets. And this collection of data sets often has an more or less obvious network structure, like a local data set being the data collected by a smartphone. And you have then 2 smartphone users nearby each other. And the statistical properties of these nearby smartphone users, for example, during a pandemic, might be somewhat correlated or similar. So we have these network edges with weights that quantify similarities between local data sets. Okay. Second component of machine learning is models. So we need a model. And here we not only have one model, but we have a separate local model for each local data set. So each local data set also has its own, for each local data set, we try to fit a separate local model. And this can be very different. So one of these local models could be a linear model. Another local model could be a deep neural network, a transformer model. Yet another local model could be a decision tree. So we also study methods that handle such heterogeneous collections of very different local models. Okay, so what is specific about the models that we use here in federated learning is that we somehow couple these models, these local models. We use the network structure of the data. So we use these edges here that indicate similarities between local data sets to couple the training of local models. In particular, we want local models that are connected by an edge to be not too different. So we want to couple them somehow. And one way to couple them is by penalizing the difference, a large difference between the model parameters. Of course, this here only works if we have parameterized models. So we have parameter vectors that we can compare over the edge. We can form a difference of parameter vectors over an edge, and then use some penalty function that could be a norm or a squared norm to measure this discrepancy. And in the end, we want to keep this discrepancy small. It's a form of regularization, actually. Yeah, so here we already arrive at this total variation concept, or the notion of generalized total variation, where we just sum these discrepancies over all edges. So this is just the sum over all edges, and we sum these differences in the local model parameters weighted by the edge weights. So if an edge has a high weight, then there's a big focus on keeping the difference over this edge small. So coupling, a strong coupling of the local models over that edge. Okay, so here, this is already a design choice, this penalty function. And I mentioned here two such penalty functions. One is the squared Euclidean norm, which is used in one of the first or seminal paper on federated learning, which proposes a method called MOCA, which I still didn't find out what the full name is of this method. I only know this abbreviation MOCA. Another special case is obtained for using the Euclidean norm as the penalty function, and this is typically known as network lasso. So it's wrong. It's not lasso, it's network lasso. Okay, so far so good. Just see if there are any questions at this point. No questions yet. Yeah, so these special cases here, they only work for parameterized local models. So parameterized local model could be linear regression, logistic regression, a generalized linear model, whatever you can parameterize with the same number of parameters. Otherwise, if you don't have the same length for the parameter vectors, you cannot compute the difference, of course. So this is somewhat restrictive. And here we have recently looked at an extension of this concept. So that's why we call it generalized total variation, because we can also define a variation for arbitrary two local models that are connected over an edge, and this, or more or less arbitrary. They must be somewhat compatible in the sense that they use the same features or the same choice of features of a data point. But for example, one model could be a linear model or a polynomial regression model, and the other model could be a decision tree. So this allows to compare a decision tree and a linear model. And the way we can compare it, well, you compare models by how they predict on a common test set. Is one way to compare models. This is also similar in spirit to knowledge distillation techniques. So here we coupled the two models that are connected by an edge, by requiring them to have not two different predictions, to not deliver too much varying predictions on a test set. So we want these two models to have the same or similar predictions on a test set. And this test set must be shared between those two local data sets, of course. Okay, so now I talked about network data, network models. So we need the third component, of course, which is a local loss function. And this can be anything ranging from an average loss so like an empirical risk, to something that you derive from a likelihood function, so might also be obtained from fitting probabilistic models. But in the end, we just need some loss function. So this is an abstraction that hides away the details how you fit the model to your local data set. Okay, and yeah, here we go. We just plug everything together. So we want to find, we want to learn local hypothesis maps. So these are this HI here. We want to learn local hypothesis maps that on one hand have a small loss for each local data set. So we want to fit them. We want to fit each local model to its local data set. This would be something we could do independently. So if we wouldn't have this second term here, this sum would break up into independent trainings. So this would be plain old machine learning for each local data set separately. So how we couple this is by adding this regularization term, which is the generalized total variation. And we amplify, or we scale the importance of this coupling by a parameter lambda. So the larger lambda, the more we want to couple local models to be similar across the connected components of this network. So if we make lambda sufficiently large, at some point we will end up with a common trained model that is identical for each local data set. And this is one mode of federated learning. So this is related. This mode is used by federated averaging, for example, where you train one single model, so you end up with one single model for all clients, basically. However, there's some middle ground. So if we choose lambda not too large, not too small, then it turns out, and this is one of our main results recently, that where do we have this? The trained models, they will be clustered. So they will be clustered. They will be constant over well-connected subsets of nodes, for example, here and here. So if we choose lambda large enough, but not too large, then we will end up with with identical hypothesis maps in these clusters. If we make lambda too large, then basically this whole network here is considered one cluster. All right, so now I have introduced rather quickly GTV minimization as a design principle for federated learning. So most of the existing methods and algorithms that you will see in federated learning literature, they are different optimization algorithms for solving certain special cases of this GTV minimization. So here already I want to point out how we can have human agency and oversight. It's exactly here where you choose what local models you use, what network structure you use, or indirectly by these weights. So these weights here define, these edge weights define the network structure, and there are different options for choosing the network structure. And there's also a big field called complex networks, which studies which network structures are more robust to failures. So if some of the nodes fail to contribute to the federated learning algorithm because, for example, one of the nodes is my smartphone and I'm running out of battery. So certain network structures can easily cope with such failures. Yes. Is there any questions, or is it just an open mic? There seems to be just an open mic. Yes, what else? Yeah, so I want to point out here that when you write down GTV minimization, you can ensure, or you ensure human agency and oversight by these choices, by these design choices. And it should be made very clear somehow in the documentation of your app, what are these design choices? So it's not useful, it's not very helpful if these design choices are not made explicit, but you then rather write down the algorithm, like an optimization algorithm that you apply to this GTV minimization problem. Okay, so here are some special cases obtained for specific choices are, for example, as I mentioned before, the network lasso. So the network lasso applies to local models being parameterized. and using as penalty function the some norm. I guess in the original paper it was the Euclidean norm, if I'm not mistaken, the 2 norm. Yeah, so this is the network lasso. Another special case that I already mentioned is the MOCA. Also in MOCA, we use parameterized local models. So we have a parameter vector for each local data set, but they use a different penalty function. It's a squared Euclidean norm. And here, compared to the network lasso, which uses the norm, so this is somewhat similar to the distinction between ridge regression, which uses the squared Euclidean norm for regularization, and the lasso, which uses the 1 norm. So the analogy is that the lasso, which results then in variable selection behavior, so it results in having only few weights being non-zero. Here the analogy is in network lasso, there are only few edges across where the weight vector changes. Or in other words, the network lasso tends to cluster the weights. So it results in piecewise constant weight vectors. Okay, yet another example that we recently looked at is using as a variation the discrepancy or the squared error of the difference in predictions on the same test set. And we are basically free to choose whatever local model we want. So this is then what I call model agnostic federated learning. So here you can train whatever you want. Some nodes, some clients use decision trees, other clients use a pre-trained neural network or fine-tune a neural network. Yet other models use a linear regression model. However, we can still compare them or couple them by require them to have similar predictions on a common test set. Okay, another special case is convex clustering. So in convex clustering, we use as penalty P norm, so P larger or equal than 1. So this is a generalization of network lasso, some P norm, and the loss function is obtained by the squared Euclidean distance to these reference points. So here the goal is to cluster a given set of observation vectors, AI. Yeah, so convex clustering is yet another special case of this GTV minimization design principle. There's a question. What is the difference when you use WI and HI? Very good question. So when I use WI, then this is a vector. So when I use W, this is always a vector with a given fixed dimension. And when I use HI, then this is a hypothesis, an arbitrary hypothesis out of a very abstract hypothesis space. Yeah, very good point. So I used, okay, and then here, of course, there's a typo. Here should be H. So we optimize the local hypothesis maps here, no weight vectors. So here in this heterogeneous federated regression, we might have non-parametric models. No parameter vectors here are needed explicitly. Okay. Yes, another special case of this GTV minimization is actually locally weighted learning, where we use as penalty function indicator functions. So as penalty function here, we use this penalty function here in GTV minimization could be an indicator function that is 1 if node J is within a certain neighborhood of node I and 0 otherwise. And what you then obtain from this choice is a perfect pooling of local data sets in order to train a model for each node in this cluster. So this is locally weighted learning, which is not too recent as a learning principle. So, but it's nice to reobtain this established learning principles as special cases of GTV minimization. Okay, so before I continue with some nice duality results or characterization, I must place some assumptions. Let's say for the sake of exposition, from now on, for the next slides, I only consider parameterized local models. So that's why I use the W's again. So we have a parameter vector for each local model, and we use some norm as penalty. In particular, I don't allow a squared Euclidean norm. So we need to use a norm as penalty. And the local functions, the local loss functions, they are convex and differentiable. So this is somewhat restrictive, but nevertheless, it might be useful working assumptions to explore a nice duality, which was in the center of my recent research a lot. So it turns out that this GTV minimization has a dual function, in a very precise sense, a dual function, particularly using a convex duality. And this dual function is a network flow optimization problem. So solving GTV minimization is equivalent to solving this flow optimization problem, where we optimize. So instead of optimizing the local parameters of a model, we now optimize flow vectors. So each network link is assigned a flow vector, and we optimize the flow vectors under flow conservation constraints. So this opens up, of course, immediately all the literature, the rich literature on network flow optimization methods. And also what I like about this, and maybe this could be called transparency. So if you like these characterizations of systems by optimality conditions. So we have here this primal dual optimality condition, and this looks like this very structurally resembles what I have learned a long time ago in high school as Kirchhoff's law. So this, or a special case of Maxwell equation. So these flows, they must be conserved. And the only way for these flow vectors to leave or to get injected into the network is via the gradients of the local models. So the gradients of the local models evaluated at the trained, at the finally obtained parameter vectors, these gradients are the injection or the leakage of flow that runs through this network. And the flow vector also satisfies this condition, this optimality condition, which tells us if you use as this penalty function is a norm, so the dual of this penalty function is then an indicator function of another norm, of the dual norm. So this optimality condition, which is somewhat like an Ohm's law, an abstract Ohm's law. So it tells us how the potential difference across an edge is related to the flow through that edge. And this Ohm's law tells us that the local parameters can only change over saturated edges. So only those edges which we can saturate by flow, they allow for different parameter vectors. On the other hand, for any edge where the flow is not maximum, doesn't saturate the capacity of this edge, the attached weight vectors on both ends must be identical. So this means that the parameter vectors over unsaturated edges, they form clusters. Okay, so for me, this would be one example of transparency, because I can relate these properties of GTV minimization to concepts that I have learned. So, but those of you which didn't learn Kirchhoff's law and circuit design, electric circuit design in high school, this might not be an explanation. But for me, this is nice, and I could say it's a form of transparency. But I will then quickly, let's see if I need to speed up a bit. Yeah, I will quickly glance over another more principled approach to transparency. So here, this flow perspective also allows to study conditions such that the learned weight vectors are obtained from pooled local data set, because enforcing identical local parameter vectors over nodes in a cluster is equivalent, almost equivalent, to pooling the local data sets in the same cluster. So, and this pooling means that we collect small local data sets and end up with sufficiently large training sets for each local model in the same cluster. Because I guess many of you know this rule of thumb, to train a model with D parameters or D design parameters or degrees of freedom, you need to have at least D training samples. So the local data set size might be much too small to train a deep neural network. However, in this GTV minimization, the effective sample size is the aggregated sample size of all the nodes, all the local data sets in the same cluster. And this might be sufficiently large to ensure robust training, or in other words, to avoid overfitting. Okay, and so this is related to technical robustness and safety. Yet another aspect here is that the network structure itself could be designed to make it maximally robust in terms of these network flows. And there's, of course, a large and rich literature about how different properties of networks, or how they are formed, network formation dynamics, result in different types of robustness or resilience against different types of attacks, random attacks or targeted attacks, where you actively choose which local data set or which client you want to kick out of the network. Okay, yes. So now that I talked about this basic duality, and this duality could be used to characterize the solutions, then the next question is, yeah, okay, but how to actually compute the solutions? So how to efficiently compute or approximate solutions? And yeah, my favorite approach always is to formulate the computational problem as a fixed point iteration. This is for me the most beautiful way to approach any computational problem. And it turns out that many of the algorithms that have been applied to federated learning applications, they are specific choices for the fixed point iteration, of specific choices for this map used in the fixed point iteration. So if you use here the gradient, basically, then you obtain anything related to gradient descent or stochastic gradient descent if you use stochastic gradients to build this map. If you build this map using primal dual optimality conditions, you end up with ADMM or with primal dual methods and related variants. Yet another example, which is I like very much at the moment, is block coordinate optimization. So here the iteration, or this fixed point iteration, has a very appealing form, in my opinion, that at each iteration, each local data set does basically empirical risk minimization. So at each iteration, each node does empirical risk minimization, where the regularization term is obtained from the other's weight vectors. So we use the other weight vectors to regularize the local training problem. And it turns out, you can show that if you repeat this sufficiently enough, and the local loss function has nice properties, then even when you have stragglers or link failures, which mean you can do these updates only or you can do this local training only with outdated information. So this W hat here, this local parameter vector of a neighbor, might not be from the previous iteration, but from 10 iterations before, because this client was out of reception or you didn't have a Bluetooth connection then. So this is related to asynchronity. And it turns out that if this update here is a contraction on the max norm or supremum norm, then this fixed point iteration, FedRelax, converges for any delay. Or let's say you must have an upper bound on the delays, but it can be arbitrary. There must be a fixed upper bound on the maximum delay, but it can be arbitrary. And still, if you repeat this iteration sufficiently often, you get closer and closer to the solution of GTV minimization. And this is also nothing brand new, this theory behind it, but it's based on, or you can find the results of this type in the textbooks of Bertsekas, which is, I would say, my favorite Greek, current Greek. Okay. Yes. So maybe I'll skip this here. Yeah, briefly mentioned this requirement for privacy and data governance. So in this update for this FedRelax algorithm, you see that we use information from other nodes. Here, when we when we use the model parameters from the other nodes to form this regularization term, here we might leak out information to other nodes. And there I just found a very relevant paper. It's not too fresh, so it's 2011 GMLR paper, which actually characterizes how much we must perturb the solutions of this optimization problem, or it provides exact means or somewhat precise means for how much noise we must add to this optimization problem to ensure what is called differential privacy. So there's this notion of differential privacy, which I will not explain in any detail now. It's just a quantitative measure using a specific probabilistic model for privacy protection. But I find it nice that this naturally comes out from using this Federal X algorithm, which formulates these updates as empirical risk minimization or regularized empirical risk minimization. So now I should speed up a bit. Yeah, so the last requirement I want to discuss is transparency. And here I want to point out again, this requirement in this position paper is formulated as AI systems and their decisions should be explained in a manner adapted to the stakeholder. And this we have translated recently into subjective explainability. So we assume we have some information about a user, which I call user signal, and this user signal could be very different types of information. Could be answers to a survey. You often get asked surveys nowadays, and your answer to a survey provides a user signal. Another more spooky or science fiction-like user signal is some AI method decoding your brain signals or decoding your facial expressions, which might be actually already used for lie detection at the borders of Europe. So there might be some way to get user signals, and one way to measure this subjective explainability we have proposed recently is via a conditional entropy. You can think of this conditional entropy as measuring how much variation a hypothesis has for data points with the same user signal. So this means for data points that you as a user would consider, well, they are the same. These are different images, but somehow they show the same thing. So the hypothesis or the predictor should give the same predictions, but it might not. So it might vary. The predictions might vary. And this variation is exactly measured by this conditional entropy. And there are ways to make this precise under suitable probabilistic model again. But it turns out that this is nothing but a regularization term. And in particular, this regularization term could be implemented via this variation measure. So we could have some nodes which represent the user or user signal. And this variation measure is obtained by using a test set that contains test data points which a user would consider similar or identical in certain aspects. So the user signal would be constant for this test set. So what we could then use is the variation of the predictions on this test set as a regularization term within GTV minimization. So this is somewhat, I would say, a quite elegant way to bring in explainability to this GTV minimization framework. Okay, so that was basically my talk. Just to wrap up, yeah, I have introduced GTV minimization as a flexible design principle for federated learning. I have discussed the different design choices for local models, the network structure, and the variation measure that allows, so if you suitably use these choices to implement or to ensure these key requirements for trustworthy federated learning. Okay, thanks a lot.
Okay, thanks a lot for a really interesting talk. Any questions from the audience? So it seems that we have at least one question.
Yes, so there's a question. Take OpenAI as an example. If the provider cannot share the weights to each client, but clients also want to preserve privacy, is this problem still related to federated learning? So Yeah, I mean the provider. So I'm not sure I understand the question here. The clients want to collaborate with each other or using a server. Maybe if Jen, would you be willing to elaborate? Yes, so the client just want to use the model to get answer. Yeah, I mean there are ways, but the server doesn't want to share the model parameters, but only delivers the predictions. Yes, OpenAI wants to, so the comment here is OpenAI wants to use the data to train their model. Yeah, I mean, if you basically when you register to OpenAI and enjoy the conversations, I guess you freely share whatever you might leak out in this conversation. So I'm not sure how to measure differential privacy there. So in this this differential privacy is, as I understood it, only a guarantee to protect from spotting if a certain data point was contained in a training set. And I'm not sure if this is related to the privacy that is referred to here. Yeah, I'm sorry, cannot provide you more about this.
Okay, so while we wait for other questions, I have a short question. So it seems that these clicks have a quite as large effect on constraining the different models. So I wonder, is this sort of like a real effect, and should the clicks be perhaps downweighted so that they wouldn't sort of, I guess, lock the models so strongly?
The clicks for ChatGPT.
No, for the federated learning. So when you have this network, and then if you have a click, let's say a triangle, it seems that you basically count the constraint 3 times. And I wonder, should that be then down-weighted?
In general, this clicks, this was a toy example.
Yeah, sure.
That are shown here. And in general, you might not have such nice clicks. So what we typically want is a sparse graph. So ideally, only a tree structure, a bit more than a tree should be already enough to have sufficient connectivity in the click. So this was a very pathological example. In practice, you might not have clicks. So I don't see this as a, I mean, having too many edges means too much more computation. It might be unnecessary computation. But on the other hand, the more connectivity within the click, the more you couple the training together, and the more you ensure that you share beneficial, actually.
Okay, thanks. I think Antti Honkela has made a comment on the chat.
Yes. So there's a comment to the previous question. Differential privacy works on aggregation of data from many users, but cannot be used to protect individual users' data while keeping it somehow usable. Yeah. Yes, any other comments or questions?
Hi, can you hear me?
Yes.
I have a question. I don't know if I understood everything perfectly, but what I see here is like we have a network that works in one level, in a kind of a large level as a whole, and then we have small, we have the nodes where there are different models, no, specific perhaps, and then all contribute to the whole, and I guess vice versa. I am a consultant from an AI company, and we have these cases where we provide IoT solutions. We train and retrain models in a large scale from different countries, for example, and we want to deliver a specific model for a specific country. And the question is, how do you deal with the data? Because the data also can be aggregated in one federated repository and use it as a whole. But then when we come to the, for example, specific country, we train the same whole huge model with that data. So yeah, I want to check if how this approach that the federated learning match the approach that we are currently using in, for example, in this MLOps point of view, because this is what I describe is kind of in MLOps what we are using for deliver predictions for different countries or clients.
Yeah. So I'm not sure I understood the question. Do you
yes.
mean it might be sometimes beneficial to not do this distributed optimization and just error? Yes. So
yeah,
if
exactly.
you know the network structure, if you have the bird's eye view of the network, or you know, basically you have all local data sets from the same country, from Austria, for example, and you know, okay, they have all the similar statistics that I'm interested in, bring them together and train a single model. Yes, that might be the most efficient way. But what we are looking at are application domains where this network structure might evolve over time. So you never really have this overview which data sets should belong to the same, should you pool together. So this pooling is done adaptively on the go while you train the models locally.
Mm-hmm. And but while you train the model locally, you are getting different predictions globally, no? So
yeah, I mean, this is our one use case is to have at each node. So I'm taking the egoistic perspective here. I want to learn a model for me. I want to learn the best model, fitness trainer app or recommendation app. Mm-hmm. But I want to use or exploit as much information from others that I have maybe Bluetooth connections to as possible. But the ultimate goal is not a global model, but each one or each smartphone user, each app user wants his or her optimal model. So my perspective is more the local training of a model, and we want so it's personalized machine learning in this case. This might be conflicting or might be a different requirements for, or might have different requirements than when you want to train a model for a whole country.
Yeah, no, I see that it's a good answer because I see the trade-off between global and locality. So this is something that I guess we have to take into consideration. Always, yeah. Okay, thank you for the answer.
Sure.
Okay, so in the interest of time, let's close this session. And thanks a lot for Alex for a really interesting talk.
Thanks a lot, everybody. Thank you. Thanks, Markus.
Thanks. Goodbye.